Okay, thanks very much. It is really grateful. I'm really grateful to be here to have a chance to be here to talk about our recent work. And this is about the field work modeling of the geomagnetic field. So we know that Earth's magnetic field is very important. That is important. Okay. So it is important in the sense that it is the survivability of the human being. It is relies on the protection of Earth's magnetic field. But on the other hand, on scientific level, the Earth's magnetic field is a unique or perhaps the only field that is generated by the dynamic system of Earth and connects with all other systems, subsystems, so which involves the Earth's core, mantle, ocean, crust, ionosphere, and magnetosphere. So those systems are connected together. So on the right-hand side, we have a sophisticated schematic plot of the spacecraft that is considered to be the outer boundary of our study. I'm wondering. So, sorry, this is considered to be the outer boundary of our study. And showing on the right-hand side, this is the plot of the geodynamo. This is the inner boundary. So Earth's magnetic field, we have studied the result from the balance. It was very dynamic balance between these two. So thanks to the new satellite, MS-1, and we have the continuation of the magnetic data, which allows us to further and continue study the geomagnetic field. So we know this is a very complicated problem. It results in very dynamic interactions. But to begin with, let's say we all believe, I believe, at least I believe, this is a very sensible assumption. The first equation on the top, we can represent the magnetic field as a great scalar potential field. In the vast region of the universe, there's no current. Therefore, we can assume this area can be approximated as a insulate. So therefore, the gradient approximation, the gradient field approximation is valid. But then the second level is that once we have the first representation, let's just represent them in a coordinate system. It's natural to use the spherical harmonics in the spherical geometry. Then there are four different terms. Here I use the model given by Nielsen in 2000 to begin with, because our model at this moment has also similar 1 month data. We believe it's sensible to start from this one. So the first term on the, okay, so 1, 2, 3, and 4, okay. So the first term is for the internal source, and following that is external, and then the first line on the top is the static in time, because we are considering a very short period. But then in that small short period, there are some fast dynamics, which is given by the DST index, which involves the variation of the ring current and the mantle induction. Okay, so from the assumption which we learned from Nielsen, then is that then for the time varying in a very short time period, so the ring current is a major source. So that's our focus. Therefore, at the current stage, we believe, first of all, we need to do two things at the same time. The first thing is to understand our data, the characteristics of our data. And second thing is to begin to understand the secondary effect, the leading order of the secondary effect, which is given by the DST. Okay. So what we did once we have the data, it's about 1 month, and then we use the equation 1 to quantify to quantify the accuracy of our work or the quality of the data by defining the so-called misfit functional J. This is in a standard least square sense. The E inverse of E is the matrix, so that is the error covariance. And at the moment, we don't have that solid in hand, so I just write it as a grid. For this work, we just ignore that. We also, okay, I'm going to talk about that later. So once having this equation, and then we use for the method we compute is based on the gradient quasi-Newton method. Then we try to minimize this quantum event to get the Gauss coefficient. Okay, so that's how we do it. The first purpose of our study at this stage. And second one is that the ring current. The ring current we think is important. So that one I'm also going to talk about relative details. Then okay, so for the quality of the data or what we have learned so far is given by these slides. So first of all, we think we have to do the data selection, and it's very critical to the result. Then, for example, the magnetic quiet time has to be chosen at night, and then the field time-dependent part cannot vary too rapidly. For example, the DST cannot go beyond 2 nanotesla per day. Considering the time variation, it's a set of the data selection rules we have to follow. Then our approximation, linear approximation to describe the ring current is valid. Otherwise, the nonlinear effect will kick in, and then it won't be that simple. So we minimize the functional, and then so of course here I use different methods. I have a relatively strong computational background, therefore we don't use the matrix-based algorithm. It's all matrix-free. It's very efficient for the computation, but on the other hand, you have to do quite a lot of iterations here. Then clearly we see after using those selection rules, we are capable of distinguish the three important components for the internal field, the external field, and the time varying part. Then it's all accurately shown. So the last, this plot on the bottom is a comparison between our model and the CAS7. Then the CAS7 from the data I have the plot is given by the red one. Then I use our assumption because our model is much simplified than the CAS7. So we get this blue curve, and then we use a mixed data of the MS1, MSS1, and a swarm data to get the green curve. Up to here, the degree 12 of about 12, 11 or 12, the agreement is quite good. But then here, we are not entirely sure what does this mean, because after all, our model is much simplified. The physical model is much simplified than the CAS7. However, then those retrieved field really describes the large scale magnetic variation to a very high accuracy. Then, of course, we are very in this sense, we are very confident about our model, and then we will further develop the of the data. Then we will further develop the model to cope with to better use of this data. Okay. Then, of course, another important thing is the model error. How we handle the model error. This is what we learned from Nielsen from his initial model from the Oyster satellite in 2000. Then in the HB3 theory developed by Richard, then it's accurately described the model error or the let's say the instrument error and the observation error. Basically, it's attitude control. So that is given by the plot on the left-hand side. And then we try to reproduce that using the data from the website given by Nielsen. Then this is our reproduction. And we believe these two plots are quite identical in terms of the error distributions. So we start to understand the importance. By doing so, we start to understand the importance and how to control the numerical, the error from the measurement and also from the attitude. Soon we're going to put that in our MS1 model and to try to repeat what we have here. So this is the first part about the data. And the second part is about the ring current. So I think you have noticed that I changed a little bit of the title is because we're kind of under a debate for quite a while what we want to do with the external field, with the ring current. So the first one to the absolute left is a reproduction of the T89 model. That is a empirical model, pretty much similar to the GFM1 or the Car710K or something like that. Then it has a description of the space current in the magnetosphere. So on the top, which facing the sun, you have two big eddies. Those are the Chapman-Ferry current. And in the middle, that is a ring current. And then on the tail, that's a tail current. These three big important current systems comprise the Earth's magnetosphere. Then this, of course, our work can be based on this part. This is very elegant description, but however, I have to give you a little details of that. The magnetosphere is a huge area. So start from the center to the Chapman-Ferry, it's about 10 to 20 Earth radii. It's a very big, very large area. Then given the size, but our measurement is somewhere here, very close to Earth. So therefore, that's a very small area. So in terms of the volume, it's about 0.1% or even smaller in comparison with the size of the big system we are looking at. So therefore, it's inevitable. We have the big arrow over there. If you want to feed the data on the other side to the large currents, these three big large currents, it's inevitable. You're going to introduce the arrow to the near Earth region, and we don't know how to control that. After all, this is not our field. But on the other hand, so we can also do something different. We can start from the first principle. So I just give it a try. Then it's it is the MHD equation, the standard MHD equation, but I did some oversimplifications. The flow is compressible, but I say it's incompressible. And then in the gray area, so showing those terms in gray are supposed to be 0, but I said they are very small. Okay, so I start to iterate the system. Then I try to see at the equilibrium state, what does the system look like? Then so here's what we found. So in the middle, this is by someone else studying, and then our result is shown here. So we believe there is a quantitative agreement. To reach this point isn't very difficult, but we are far, far, far away from the reality. So we think this could be also a good direction where we want to go. So then I look forward, maybe later on we can have a talk, then have a discussion on this topic later on. Then, of course, now let me just quickly wrap it up. Okay, by far, we have observed we see the magnetic data, and we start to understand the complexity of the data. It is highly dynamical, and the different physical processes can be seen from there. And of course, we are also limited by our quasi 2D limitations. Using the 2D observation, and you want to reconstruct a large area. This is already a very complicated problem. So, well, in the future, I was hoping to design, to develop together with all the colleagues here, to develop a more complicated and comprehensive mathematical and numerical model for the study. So, and also the space current topic, which was not the traditional topic in the geophysics, but it has been well studied in many other areas, for example, like space physics. And we are not very familiar with that. So shall we just think about the strategy, how to collaborate? Then, of course, importantly, as the #1 mission of our study is to confirm the quality of the data and then the initial result of the MS1, based on the MS1 observations. then really look forward to collaborate with everyone and to work together in the future. Well, thank you.